So in this video, we're going to talk about actually charging a capacitor, putting charge on it, as well as the energy then that is stored on there. So once we have a certain amount of charge, we can talk in terms of energy, because eventually that's what we're going to want to focus on, is how much energy can we pull out of an electrical circuit. But to understand charging, you need to understand that we have to have a potential difference in order to move charge. If there's no potential difference, no charge can move. So just thinking back to the last video where we had this, a positive, if you put a positive charge here and then you have a negative down below, this creates a kind of a downhill. We get these potential differences. So we'll get kind of a hill is how I was describing it, which then goes into a hole. But we had basically it was like a big hill, if you remember that. Hopefully, should have just been not too long ago. And so the idea is then if we have an electron, which is what we'll be talking about a lot, then the electrons, remember, go backwards. So they move towards the positive. So as long as I have a potential difference, and in this case the potential difference would be measured from here to here. That would be my potential difference. If I can produce this, then I'll get movement. Charge will be able to move. And so it's easy to see, if you had two charges that were at the same potential, like that, we're not going to get any movement between them. I don't know if that makes sense, but it's kind of a flat hill. If you have a flat hill and you put a ball, it's not going anywhere. It's just going to stay still. So you got to have this potential difference, otherwise things won't move. Okay. So now let's think about a parallel plate capacitor. So if I have these two conductors and we draw parallel plate capacitors like that, and these are conductors, so electrons can be removed or put onto them, and that's how we build up charge. So the idea is I want to take electrons. It doesn't matter which side, but I'm gonna talk over here. So basically I want electrons to move this way. So looking back at this little diagram, I need to create a potential. Because remember, at first these are neutral. So there's zero charge, so zero potential. So to get it to flow this way, I need to have a positive potential over here. Likewise, if I want it to come, because what I want to do is build up electrons on one side, which will leave a deficit on the other side. So this over here, I want the electrons to move into it. So I know that I need to have a negative potential on this side in order to drive the electrons in. And so we can create that using a power source, like a battery. And we connect it through a wire. So I'm just drawing a basic schematic. So lines would represent wires. And what I want to do is I want to create a positive potential on this side and a negative on the other side. So this is how we draw a battery. We would draw the long side to indicate the positive, and the short is the negative side. And I'm going to talk a little bit about batteries in just a second. And then connect this to the other side. So now you can see what I've done is I've created a positive potential here that's going to pull electrons towards it. But what happens once they're in here? Because all of a sudden it's at a negative. So that would be like if the electron goes up here and then all of a sudden it's like zoop, and it's back here at the negative side. So what the battery does is it kind of acts as a pump, and it's going to pump this electron. This electron's going to get up here and it's like, all right, I'm happy. And the battery says nope, and it's going to move it through this potential until it's back here, and then it's going to fly again, okay, away from here. So it can't make it all the way around though, because there's an air gap here. So it's stuck. It gets stuck on this plate. So in essence, what's happening is we're going to rip an electron off, and that leaves a net positive here because we took one of the electrons, so it's out of balance. The electron is going to come through, hit the battery. The battery is going to pump it up, or pump it down really, into negative, and then it's going to fly away from the negative and land here, putting an excess negative. And then it just continues doing that until we have a big negative charge on this side and a positive charge on this side. But it can't go forever, because what happens when this positive potential yeah, because we have a positive charge here, so that's going to create potential, is equal to this one, well then it stops, because now we're flat again. There's not enough. You have a positive here and a positive here. And so it'll stop when this potential difference across the battery, across the capacitor, is equal to this potential difference across the battery. When these are the same, there's no more movement, and the capacitor is charged. Okay, so let's focus in on the battery and what the battery is actually doing. And we're gonna do more later in the next week or two on batteries. But I just want to point something out because it's going to be important when we talk about energy. So I'm just going to zoom in on the battery. So the battery has a positive and a negative. And the idea is an electron is going to enter into the battery. And I'm kind of oversimplifying this. And the details of how this actually works you'll pick up in chemistry. But we can talk enough about it. Okay, so the idea is it's at a high potential and we got to push it over to a negative potential. And electrons do not want to go to a negative. So that means that through some process, and most batteries it's a chemical process, we're going to push this electron across. So we're going to force it to go all the way over here. And since we're forcing it to go against its nature, we're doing work on it. So the battery has to do work. And so if we remember, work is the negative change in potential energy. Don't get thrown by the negative. It just means that if I reduce the potential energy, I did positive work on it, or the battery, or the field, or whatever it is. It's just the opposite sign. If we increase the energy, then we did negative work. All right, so the battery is going to push this through a potential difference. So we have this potential difference from the positive to the negative, like 9 volts or whatever it is. And then we know a relationship between potential energy and potential difference. The potential difference is the change in potential energy divided by the charge that's moving through. So if I multiply that across, I get the change in potential energy is Q times the potential difference. So that's nice. It makes it easy. If I just know the potential difference and the charge, I can tell you how much the energy changed. But now we can substitute that in. So I get the work done by the battery. It's going to be negative Q times delta V. And the negative, again, that just indicates, whether it's doing positive or negative work. Not important here. The important thing is the amount of charge that goes through the battery will determine the work. So we could even just write it as this, like the work of the battery is going to be the charge that has to move through times the potential difference. So this is the work done by the battery, little VAT. So when we're building up charge here, positive Q, I'm sorry, that should be negative. Negative Q and positive Q over here. To determine the amount of work it did, we just need to know the amount of charge that's there. How much charge do we have to put on it? Or, you know what, let me take that back, strike what I just said. This would be the amount of charge that's moving through the battery. The amount of charge that has to go through the battery, we could determine the work from that. And we'll come back and talk about that in just a second. Because now what we want to talk about is the actual work to charge the plate. So this is just the work to move charge through the battery, but now we want to talk about work to charge at the plate. Oops. Alright, so the work to charge a plate, or a capacitor. Okay, so again, I'll just draw a little schematic. So we're going to take a capacitor, we hook it up to a battery, and then we flip a switch. Or once we connect it, stuff's going to start flowing, and it's really, really fast. So what we want to think about is I want to charge this up to Q. I want the charge on, this would be like negative Q and positive Q. So I want to charge the capacitor up to Q. So we know that the capacitance is Q over the potential difference. So if I move that over, we get the potential difference, is equal to Q over C. Now going back, if we think about this, the work as we're moving charge onto it would be the potential difference times a little bit of charge. I'm going to call it dq. I'm going to get into some calculus right here because, you know, some people are always asking, like, where does this equation come from? And I'm like, well, it's calculus. And there are a few students in here that can use the calculus, but you can kind of skip it if you're not in calculus right now. And I'm getting this from this right here. This is the potential difference times Q. That's work, right? Okay, so what we're doing is we're putting, over time, we're putting on all these little Q's, right? These electrons. So they're going onto the plate. So it's increasing by a little bit. That's what that means. So dq is just a little bit of charge. It's a little charge. It's a little piece of it. And as I keep adding these up and up and up and up, eventually it will become big Q, the total charge, and that's when it stops. You can kind of think about it like as time goes by, the amount of charge that's on it. So I'm going to have some maximum here. So what happens is it kind of does this. So I'm adding all these little dq's, and it adds up to this total. Okay, so now we can substitute, because the potential difference is Q over C. So the work done to charge to Q, and that would be over C, with respect to some little q. And this is where we need the calculus, because of this little dq. So this is calculus, don't have to know it. This is what it looks like. We're going to charge up the capacitor from 0 to Q, and it's Q over C with respect to Q. So we're going to integrate this with respect to Q. So the C is a constant, so we get 1 over C. We can pull that out, and then we would integrate from 0 to Q with Q with respect to dq, with respect to Q. So those of you in calculus, you know that when we take the integral, we do the inverse power rule, so we're going to knock that up one. So that would be Q squared, and it'd be 1/2 of that. And then I can simplify this. So the work done to charge this thing is going to be Q squared over 2C. So the work to charge a capacitor, let me rewrite it up here. So the work done to charge this capacitor is also the change in potential energy. So how much energy is stored? Well, it's the charge squared divided by twice the capacitance. And that's how much energy is going to be stored. It's also the amount of work that's done to charge this thing up. Now the thing is, we can rewrite this. There's several forms that we can rewrite this using some algebra. And one would be to substitute in for C. So let's do this. So the change in energy, let me write it like this. So remember that C equals Q over potential difference. What I'm going to do is just substitute. So we end up with Q squared over 2 times Q over potential difference. And what I can see here is that I'm going to multiply this. This would come up top. The 1/2 comes out, so we get 1/2. And then I'll get a delta V up there, and then this Q cancels out one. So we'll get 1/2 of Q times the potential difference. So that's how much energy is stored in the capacitor. That's the change in energy. And I want to focus on this right now, because how much work did the battery do? So if we go back, we can see that the work of the battery is Q delta V, but the energy that went into the capacitor is only 1/2 of that. Like, we could rewrite this. The change in energy of the capacitor is 1/2 the work done by the battery. So what does that mean? Well, it means that the battery is going to have to do a lot more work to fully charge this thing. In other words, half of the work that the battery does actually ends up in the capacitor. The rest of it is being given off by like heat, through heating process. And you got to remember, like, we're pushing electrons through this wire, so you got to overcome that. There's some kinetic energy that's in there, and then you're going to get thermal energy, and so you're going to have energy loss. Energy is going to flow out of this. Now, a lot of times we consider these things to be ideal, but in reality, we're always going to lose energy, and it's interesting that it comes out to be exactly a half for a capacitor. But this is the what their law of thermodynamics. We can't get more energy out than we put in. We can't even get equal. Like, that's a perfect ideal world that lacks like any kind of semblance to reality. So know this, that the battery is always going to have to work twice as hard to put the energy into the capacitor. All right, so we have a couple different ways to write the energy that's stored in a capacitor. Remember that Q is either one of these because it's equal on both sides. That's what it's talking about. And that's what we refer to as the energy stored in the capacitor. Although, remember, the total energy, or the total charge, rather, I think I said energy. The total charge is 0. So we just talk about the charge on one of them. There's another one. It's on your equation sheet. So any of those, and we can determine it. But okay, that's how charging the capacitor and the energy stored.